Okay, thank you for introduction. So first of all, I'd like to thank organizers for inviting me very nice workshop today. So I'd like to introduce, I want to discuss some kind of the unified framework of the hydrodynamics and number of bosons, in particular the open system. So let me start with gapless mode in nature. So one of the popular gapless modes, so actually that this is gapless, but the pions in nuclear physics. That is well known in the particle physics. But in nature, there are many types of the gapless excitation. So for example, the superfluid phonon is also the number-Goldstone boson, and in the magnet, spin wave exists. And also in recent studies show the photon is also the gapless number-Goldstone boson. And also the hydrodynamics is also the kind of number-Goldstone boson. And the more interesting feature appear in the more exotic system like active matter system. So these are actually the kind of number-Goldstone boson. So ordinary discussion of the number-Goldstone theorem works only for this kind of system. So to understand the other system, so we need some generalization. So in this talk, in particular, I will focus on this hydrodynamics and also the open system. So this is a target of this talk. So now what is the open system? The open system is a system coupled with some environment. So this is a total system can be the closed system, but if you only focus on the subsystem of the total system, that is a becomes the open system. So the system interacts with the environment. So in the case of the quark-gluon plasma, so for example, if you focus on the heavy quarks, then so if you are interested in the dynamics of heavy quarks, that is a kind of the open system that is coupled with the QGP, that is the environment. So QGP itself, in the heavy ion collisions, the QGP itself also the open system because of radiation that's coupled with a vacuum. So there is some dissipation effect. So in such a case, the QGP also the open system. And the more exotic one is, for example, this is a flux of bars. So these bars coupled with the environment that is the air. So now the question is what is the spontaneous symmetry breaking for the hydrodynamics? That is one of the basic questions. So I will review the recent study shows actually the number-Goldstone boson, the hydrodynamics mode is a kind of number-Goldstone boson. The another question is what is the symmetry for the open system? So in the open system, so because of the interaction between the systems and the environment causes some energy dissipation and particle number dissipation. So in that case, so there is no ordinary conserved quantity. So in the Hamiltonian system, existence of conserved quantity corresponds to the existence of the symmetry. But in the open system, this does not work. So even such a case, we can define some global symmetry, and also we can discuss the number-Goldstone boson. So the question is that in such a case, what is the dispersion relation for the number-Goldstone boson or number-Goldstone mode? That is a question. So in this talk, I want to answer these questions. Okay. So yeah. So let me start with spontaneous hydrodynamics. So let me introduce the two types of the symmetry. So nowadays it's called the strong and weak symmetry. So let me start with the density matrix. So we are interested in the many-body dynamics. So it's better to consider the density operator as a state. So the system has some global symmetry G. So the whose unitary operator is written in the UG. So ordinary symmetry, ordinary global symmetry acts on the density operator like this. So under the global symmetry, so the density operator transforms to the U dagger like this. So in this talk, this symmetry is called the weak symmetry. So this is the ordinary one. So the for thermal state or the vacuum or any equilibrium state. So if this transformation becomes the original one, then that symmetry is unbroken. So otherwise, we can say this is a spontaneously broken state. So this is the ordinary symmetry breaking classification. So now, so we want to consider another types of the transformation. That is called the strong symmetry. So again, so since density operator has a you can consider the transformation from the left or right. So you can consider this kind of transformation. Then if state is proportional to just the phase, then so in this case we say strong symmetry is unbroken. So otherwise, that strong symmetry is spontaneously broken. So that is a kind of definition of the strong symmetry. So obviously, when weak symmetry is spontaneously broken, then the strong symmetry is also broken. But in hydrodynamics, actually the ordinary hydrodynamics corresponds to the strong symmetry is spontaneously broken, but weak symmetry is not. That is a hydrodynamics. Yeah. Example. I will show you the example of the other hydrodynamics. So the vacuum state, obviously, usually invariant under any global transformation. So this is a vacuum state is invariant under the strong symmetry. Yeah. Usually, yeah. So if this is a pure state, then this is invariant. But ordinarily, the mixed state is not invariant. So in particular, we are interested in the grand canonical ensemble. So obviously, this state is not invariant under the strong symmetry, because this state mixes the energy and particular numbers. But that's still invariant under the weak symmetry. Expect the Lorentz symmetry. So actually, the thermal state breaks the boost symmetry. So except this symmetry, usually, yeah, this satisfies. Depends. Okay. Yeah. Sure. Yeah, okay. Yeah. Yeah, that's a good question. So actually, okay. So microcanonical, so grand canonical is actually a kind of the explicit breaking. So this state is explicitly break the strong symmetry, but the microcanonical, so that is a fixed number and fixed energy state. So in that sense, this is naively thinking that is this has a strong symmetry, but still that state is spontaneously breaks the strong symmetry. This strong symmetry. So I will explain the next slide. Yeah. Yep. Standard things. Yeah, exactly. Yeah. Right. Yeah, that is the ordinary symmetry, the weak. Yeah. You mean the unbroken case or broken? Yeah. Okay. So if so okay, maybe yeah. Later, yeah, it's more clarified. So before that, I want to clarify the other parameter. That is nothing but the susceptibility. So this is just a definition of susceptibility. So yeah, J0 is a charge density. And so usually the thermodynamics, this value is non-zero. But if the state is the eigenstate of the charge, then naively you can say that this becomes a zero, right? So, but usually thermodynamics, this is not the case. So even the microcanonical ensemble, so the local operator gives the same value as the grand canonical. So if you calculate this value, then it becomes non-zero usually. So in this sense, the microcanonical ensemble breaks the strong symmetry spontaneously. Yeah, yeah, yeah. Yeah, yeah. Yeah, yeah, exactly, yeah. Yeah. Yeah, yeah. But I must say that this integral does not commute with the expectation value or something like that. So, so if you just focus on the local two-point function, then integrating over the volume, that gives you some non-vanishing value. But if you calculate the so this fixed charge number, but that operator is not very defined because the volume is infinite. If you take the volume infinite, then that operator gives you some infinite number. So in that sense, this operator is somewhat ambiguous. So this is similar to the ordinary symmetry breaking pattern, right? Yeah, ordinary symmetry breaking case is also happened some kind, yeah, this phenomenon. Yeah, expected value, yeah, in some sense, yeah. Hmm? Yeah. 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 Always spontaneous symmetry breaking phenomena, some strange things happen, right? Yeah. Yeah, no. Yeah. Break. Conservation. A conservation case, for example, the vacuum state is conserved, right? Or just the ordinary eigenstate of the particle number. That is just a finite, not infinite. That state is also the conserved. But matter case is somewhat ambiguous. Okay. Yeah, any case, the recent study shows yeah, microcanonical ensembles can be understood as yeah, spontaneous breaking of the strong symmetry. So now, yeah, we want to discuss the effective theory of the hydrodynamics. So it's better to consider the Schwinger-Keldy's formulation in this case because we treat the density operator. So here is a path integral of the Schwinger-Keldy's path. Then the original theory has this kind of path integral. So in the boundary, so we have the density operator here. So this is time evolution. So now we have the two types of the action. So that is the forward action and backward action. So if system has a global symmetry, then you can define the two types of action for the two types of global symmetry acting on the forward path and backward path. So in this path integral formulation, we have that two global symmetry. So that is doubles. So G1 and we say G1 and G2. So we want to consider the effective theory associated with the spontaneous symmetry, spontaneous breaking of these one. So if actually the thermodynamics corresponds to the this kind of symmetry breaking phenomena. Okay. In this case, the double symmetry is clear in this formulation. Okay. So let's discuss the construction of the effective theory in general case. So if you have the global symmetry G, this is a continuous global symmetry break down into its subgroup H. So we want to have the effective Lagrangian for this symmetry breaking phenomena. So we know that in that case, the degree freedom is the coset of the G over H. So, but here, so first we prepare the degree freedom for the group values degree freedom G, like this, Xi. So this is not coset variable. So to get the G over H, so we gauging the H variable. So we impose the local symmetry for this one. So if you are familiar with hidden local symmetry, this is nothing but hidden local symmetry. Then you can write down the effective Lagrangian invariant under this transformation gives you the effective Lagrangian for the G over H. That is one of the construction of the effective theory. So the other example in the vacuum, so let's consider the chiral symmetry breaking. So in that case, we have the SUN left, right, and SUN right, SUN right times SUN left. That is a chiral symmetry. In the vacuum, QC vacuum breaks down into the diagonal part of that one. Then we can define the element of this one given by this. Then imposing the gauge symmetry for the unbroken one, like this. Then gauge invariant combination is nothing but this one. Then you can write down the effective Lagrangian for this. This is nothing but a chiral Lagrangian. Okay. So this is a process of the construction of effective theory. So now let's apply this idea to the hydrodynamics. So since any susceptibility, so for example, is non-zero in the the thermodynamics. So which means the strong translational symmetry, space-time translational symmetry is spontaneously broken. And also the weak Lorentz symmetry is also the spontaneously broken because of the existence of matter. So this is a constraint. So then the degrees of freedom, so since this is a translational symmetry is broken, so degree of freedom is that variable, that is nothing but a kind of the coordinate. So since we have the forward and backward path, so we have the two types of the degree of freedom. And sigma is a emergent, the coordinate. So sometimes this coordinate is called the fluid coordinate or the material coordinate. Then since weak symmetry is unbroken, so we impose the gauge invariant for this variable, but still Lorentz symmetry is broken. So not complete differ is not imposed. So for example, we can impose just the space differ and for the spatial coordinate, and ordinary time differ for the time component, or just the spatial differ is imposed. So honestly speaking, so if this differ is time independent, then this weak Lorentz symmetry is actually the restored. So we cannot impose all differ invariance, but yeah, we may impose these kind of things. So this is a well-known emergent. So this is well-known the gauge symmetry for the hydrodynamics. For example, you can see the this paper. So they discuss this kind of things. Anyway, within this formulation, so yeah, this redundancy comes from the unbroken weak symmetry. That is one of the construction. So yeah, the hydrodynamics can be constructed with within this symmetry. So you can define this kind of degrees freedom. So that time derivative of the coordinate nothing but the inverse temperature times fluid velocity. And this zeroth component is just the scale of the temperature. So this combination is invariant under the previous transformation. So that you can define the action have this form. Then if you consider the Schwinger-Keldy's action, that has this kind of configuration. So in this talk, yeah. So usually, so we also impose the KMS condition or something like that. But yeah, in this talk, this is not so important, so we skip that concept. But in any case, yeah, effective Lagrangian has this kind of form. So this is the hydrodynamics for the, yeah. Yes, please. Full differ, yeah. So if you impose a full differ invariant, then this degrees freedom disappear. So actually, yeah. So that becomes the vacuum theory. So where there is nothing. This paper, yeah, this paper imposes this kind of symmetry, yeah, as a effective theory of the hydrodynamics. But they didn't say that this kind of things. Yeah, they discuss something like gauge invariance. I mean differ invariance for hydrodynamics anyway. So so we are interested. So later we are interested in the dispersion relation of the excitation. So as a simple example, let's consider the U1 case. So that is so in that case we have just a charge diffusion in the other hydrodynamic mode. So let me explain that construction. So this was discussed by these guys. So first. So in the Schwinger-Keldy's formulation, so we have the two U1, that is the forward and backward U1 case. And we have the U1 coset degrees freedom. And another weak symmetry, that is just a shift symmetry for this one. The strong symmetry definitely corresponds to the opposite shift U1 rotation. So in the so-called RA basis, that is the basis for the different combination of the 1 and 2. That is the A degree freedom and R degree freedom, something like this. So under the weak transformation, so pi A is invariant, obviously. And pi R is not invariant, but pi R is invariant under the strong symmetry. So this is a combination. So since weak symmetry is unbroken, so we impose the gauge invariance for the weak transformation. So which means the R degree freedom invariant under this transformation. And also so this is a strong symmetry is spontaneously broken. So this guy is in this case this is constant. So the invariant combination under the unbroken strong symmetry and broken weak symmetry, broken strong symmetry, but unbroken symmetry is something like this. So this is the building block of the effective Lagrangian in this case. So this is for the unbroken weak symmetry. So if weak symmetry is spontaneously broken, so we don't need to impose this gauge symmetry. So this operator is also allowed it. So that is the difference between the spontaneous broken U1 symmetry or just only the strong symmetry. Then you can write down the effective Lagrangian by using the degree freedom, gives you this kind of things. So in the Schwinger-Keldysh formulation, so the at least Lagrangian contains the pi A field. That comes from the unitarity of the system. So the effective Lagrangian is at least contain the A field. That is a constraint. Then you can write down the possible term like this. So we do the derivative expansion. So the leading order term has this kind of form. Then if you write down the equation motion, we'll get this kind of things. Then which means that the dispersion relation has this form. So that is nothing but the charge diffusion mode in this case. So if weak symmetry is spontaneously broken, the situation is a bit change. So in that case, we can have this kind of term. So that was prohibited by the gauge, unbroken gauge transformation. So, but now weak symmetry is broken. So yeah, we have this kind of thing. Then you can write down the equation motion. Then you can get the propagation mode. That is nothing but the ordinary Nambu-Goldstone boson at finite temperature. So we can understand by using the strong and weak symmetry. And we discussed the hydrodynamic mode and also the Nambu-Goldstone boson. So this is the basic thing. Okay. So now this is this work for the closed system. So now we want to move on. We'd like to move on to the open system. So the simple question is what is a global symmetry in open system? So since so ordinarily the Hamiltonian system, if you have the continuous symmetry, that means existence of the conserved quantity. The open system, this is not the case because the interaction between the system and environment causes some energy dissipation or particle dissipation. So now the question is what is the symmetry? So is there any symmetry breaking phenomena? So does the energy model appear or not? That is the question in the open system. So actually, there is some symmetry breaking phenomena even in the open system, and also that we will have some Goldstone bosons. So let me show you some exotic example only appear in the open system like this. So this is a well-known phenomena called the synchronization phenomena. So in this case, time translation symmetry is spontaneously broken. Or another case is so-called this is a condensed matter system case, the driven dissipative condensate. So this is a kind of the Bose-Einstein condensation driven by some external field. So if you put the laser or some electric field or something into the system, then the system is excited. But because of the radiation, that is dissipate. But in such a case, there is some, sometimes it causes condensation. So such a condensation phenomenon is called the driven dissipative condensate. So one of the famous this kind of phenomena is actually the laser. Laser is actually the pumped by the external field, then we have some coherent wave. That is nothing but this kind of phenomena. So another interesting phenomena is so-called behavior of, for example, the bird. So one of the famous models is called the Bichek model. That is a kind of the classical model for the like this. So you can imagine that this arrow corresponds to the some fish or bird. So this is the equation motion. So that is not so important. The important point is that if you simulate this kind of degree freedom, so this it depends on the parameter. So you can see that some randomized phase and also some ordered phase. So this kind of ordering order is, for example, this is some cell on the fish skin. So you can see some randomized phase and ordered phase. So this kind of spontaneous symmetry breaking phenomena occur in the open system. This is special for that case. So now let's go back to the field theoretical model. So one of the model for the active matter is called the so-called active hydrodynamics. So this is kind of the generalization of the hydrodynamics. So unlike the ordinary hydrodynamics, so we'll have the non-conserved term that corresponds to the open system. So if this term is absent, then this is nothing but the ordinary hydrodynamics. But now we have some non-conserved term. So it depends on the parameter. So yeah, so typically this parameter represents some friction or dissipation. But it depends on the parameter. So we will have some symmetry breaking phenomena, and the steady state have something like the non-vanishing velocity. It breaks the rotation symmetry. Then fluctuation gives you some gapless excitation. That's in this case, you have some propagating mode and diffusion mode. That is nothing but the kind of Nambu-Goldstone boson in this case. So we want to describe this kind of phenomena by using the effective Lagrangian. Okay. So the basic question is that can we, so in this case, so existence of dissipation, we still have some kind of the rotational symmetry in this case. So yeah, so we want to understand the this phenomena by using the ordinary field theory technique. So the main basic question is that can we discuss the symmetry breaking without ordinary conservation law? So yeah, the answer is yes, of course. So we can define some kind of symmetry transformation even in the open system. So to explain the symmetry in open system, so let me start with the ordinary symmetry. As a simple example, so the harmonic oscillator in 3 dimensions. So this is just an ordinary harmonic oscillator. So equation motion is just like this. Then, so in this Lagrangian is invariant under the rotation. Then you can have the net charge. It's just x cross p. This is just an ordinary angular momentum. And also that we have the momentum here. Of course, this is invariance of the action. So this is time independent because this is just a net charge. So this is the ordinary story. So now we want to put some friction here. Then still equation itself is covariant. But of course, the angular momentum is not conserved because of the existence of this term. But still, we can define the action for this system. Of course, this is a dispersive system, so the action itself is not the usual one, but you can define this kind of action by introducing the auxiliary field. So this action, so equation motion for the x bar gives you the equation motion for this one. But this action is invariant under the rotation given by this one. Then you can, so since we have the action, so we can define the Noether charge for this action. Then that is nothing but this form. And so actually, the open system has this kind of symmetry. So this is nothing but weak symmetry in the Schwinger-Keldysh path formalism. So the open system, so actually in the open system, strong symmetry is explicitly broken in this case, but still have the weak symmetry given by this kind of form. Yes. Yeah, in this case, yes. Yes, yes. Yes. So in this case, yes. But in the quantum field theory or Schwinger-Keldysh formulation, so we have this kind of degree freedom. Right, okay. But the equation itself is somewhat. Yeah. Okay. So in this case, this is an assumption. Yeah. But yeah, if you start with yeah. Yes. Yes, in this case, yeah. The symmetry, yeah, okay. So in this case, the ordinary symmetry. So if this term is absent, then yeah, this value is conserved. I mean, yeah, this one. In this Lagrangian is conserved. What do you mean by strong symmetry is broken? The fact that the derivative of NR is not zero. Derivative of yeah. Derivative of LR is non-zero. All right. So this is what you mean by the strong symmetry is explicitly broken. Explicitly broken, yes. So this, but still, yeah, weak symmetry is unbroken. Yeah, that in this case it's not clear. Yeah, it's not clear, but yeah. So actually, so if you start with a Schwinger-Keldysh formulation, so we have the Q1 and Q2. But the open system means something like the interaction between the phi1 and phi2 fields. That's coming from the environment, interaction between the environment. Then if you define the two charge, the difference and sum. So this is actually the symmetry for the weak symmetry. And this is a kind of the broken part of the yeah, this corresponds to strong symmetry. Why? Yeah, so yeah, strong symmetry is a invariance under the Q1 or Q2. That is a strong symmetry. Q1 transformation generated by Q1 or Q2, that is a strong symmetry. So originally density, we have the density operator. So that transformation acts on from the left or right. So left corresponds to the I don't know which one, but yeah, for example, the phi 1, transformation phi 1, that corresponds to the, yeah. Yes. But so originally this, so we have the density operator and here. So the action of the from the left gives you the transformation of the phi 1 field. And from the right gives you the transformation of the phi 2 field. So that is a strong symmetry transformation. So this action is invariant under the strong symmetry transformation. Yeah. Okay. Yeah. Okay. I understand the point. Yeah. I see. Yeah. Okay. I see. So in this case, yeah, system is invariant. I mean, the action itself is invariant under the strong symmetry transformation. That is a time evolution. So yeah. Okay. Yeah. So anyway, yeah. Please admit that, yeah, this transformation is a strong, and yeah, this one is a weak. Anyway. So the example that breaks the non, I will show you. Okay. The example of the explicit breaking of the strong symmetry as a model is something like this. So this is just a SU2 cross U1 model with some dissipation here, and also the fluctuation. The fluctuation is not so important here, but yeah, we have the friction term here. Then we can consider the spontaneous symmetry breaking phenomena, and we can discuss a Nambu-Goldstone boson as usual. Then the linearized equation gives you this kind of equation. So now we have the friction here. So if there is no this term, then this is just a wave equation. So we have the ordinary Nambu-Goldstone boson. But since this is open system, so we have the something like here that gives you this kind of low energy mode. So existence of this term gives you some gap, actually the damping mode and still diffusion mode. So the ordinary Nambu-Goldstone boson, originally that is a propagating gapless mode turned to the one diffusion mode and one damping mode. That is the fate of the open system in this case. So this is a model case. Yeah. So now we want to discuss we want to understand this phenomenon by using the low energy effective theory. So again, let's consider the U1 times U1 model. So again, we have the two. This is the same same as before, but now the strong symmetry is explicitly broken, which means this is a building block as before. So the strong symmetry is explicitly broken, meaning that no derivative term is allowed it. So if symmetry exists, so we should have the all degree freedom has a derivative. So this is similar to the ordinary chiral Lagrangian. So the quark mass explicitly breaks the chiral symmetry, then we have the mass term That's proportional to this kind of things. So similar things happen in the this hydrodynamic phenomena. Again, weak symmetry. Now weak symmetry is still good symmetry. So we can also consider the weak symmetry breaking. Then in that case, we have this one. The difference is just we have this kind of term is allowed it in open system. So now, because the existence of the single term here, the effective Lagrangian can be written in this form. Then you can solve the equation motion. So if weak symmetry is unbroken, then original hydrodynamic mode becomes just a damping mode. Then on the other hand, so when weak symmetry is spontaneously broken, then we will get the diffusion mode. So this is a story as this model. Yes. So anyway, naively you can think the open system, meaning that the Nambu mode becomes just a damping mode. I mean a diffusion mode. But this is not always the case. So in general, there are two types of the energy mode exist in nature. So usual one we call the type A. So the exotic one is called the type B. So let me explain what it is. So ordinary Nambu theorem in the vacuum states that for Laurent invariant vacuum, when spontaneous symmetry is spontaneously broken, then Nambu boson appears, whose number is equal to the number of broken symmetries and whose dispersion is linear in momentum. So that is the ordinary statement. But in nature, there are many different types of energy modes exist. For example, in the context of QCD, so if you go to the very high density system, so where the color flavor locking system, so that is the color superconducting phase is realized, and also the K-on is condensed, then in that case, symmetry breaking pattern is the SU2 isospin times U1 hypercharge break into the, looks like the ordinary, this is a similar breaking pattern as the electroweak. Then in that case, the broken symmetry is 3. The number of broken generator is 3. But in this case, there is the only 2 energy mode appears, and whose dispersion is linear and quadratic. So another example is a famous one is a magnon. That is just a spin wave. That is a spontaneous broken of the rotation symmetry like this. So in this case, the broken generator is 2, but it is known that the only one energy mode exists, whose dispersion is quadratic. So in nature, there are 2 types of energy mode exist. So previous discussion, so we just focus on the linear dispersion one. That's become the diffusion mode. So now the question is what happens in this type of energy mode. So just to remind you the classification of energy mode. So we say that there are 2 types of energy modes. That is type A. That is actually that has a linear dispersion, and type B that corresponds to the quadratic dispersion in general. So yeah. So this can be easy, and the main important point is for the type B mode. So 2 commutation relation between the 2 conserved quantity, the whose expression value is non-vanishing. So in that case, there exists some kind of the type B mode. So it looks like the precession motion. The ordinary energy mode corresponds to just the harmonic oscillation. Yeah, this is somewhat trivial. So to understand this kind of phenomena, let's consider this kind of classical motion. So this is a classical object, the pendulum with a spinning top. So this has a rotation symmetry is explicitly broken by the weak gravity. So since this system has a gravity, and the rotation along the z-axis still unbroken, but the x and y axis is broken, somewhat spontaneously. Then we'll have the two low energy mode. So actually, this is just like this. So this is true for if the top is not spinning. But in that case, if this top is spinning, then we'll get the spinning motion, precession motion like this. So that corresponds to the two angular moment commutation relation, so in this case, Poisson bracket between the two broken generator, the whose expectation value is LZ, is non-zero. So in that case, yeah, the two motion is coupled each other, then you get some single motion. Then that corresponds to the type B energy mode. So in the language of effective Lagrangian, that type B energy mode corresponds to the existence of the single time derivative term. So this is just this is a vacuum case or ground state case. So you can write down the effective Lagrangian by using the energy field. So in general, you may have the single time derivative term, and whose term corresponds to this term, or yeah. So the single time derivative is a play an important role in the behavior of the excitation. So now let's what happen in the fate of the energy mode in the case of the type B energy mode. So it is known that, because this is a model of the field theoretical model where the type B energy mode appears. So this is nothing but a U1 cross SU2 cross U1 model with chemical potential. Then the equation motion for the pion, one of the two of pion has this form. So if this friction term is absent, so you see just a quadratic dispersion. So even existence of the friction term, so in this case, you see still this mode is propagating with some diffusion coefficient, but yeah, still propagating. So the type B mode, even in the open system, yes, this can be, the propagation is different from the type A. So now let's consider the unification model for the effective Lagrangian in open system. So in general, so we can write down the effective Lagrangian by using the previous consideration. So now because the open system, so we have this term here, and also the type B energy mode also contains this information. So symmetry matching implies that so since this system has a weak symmetry, so we can define the net charge for the weak symmetry, and also we can consider the strong symmetry transformation. So this means a transformation of the weak charge by the strong symmetry. That gives you this coefficient. So existence of this coefficient play an important role in general. Then the equation, low energy equation motion for this operator gives you this one. Then when the solving this linearized equation, you will get some hydrodynamic mode and also the energy mode in open system. Then we can classify the gapless excitation mode following this equation motion, so that this single time derivative term play an important role. So we classify the type A by the degrees freedom corresponding to the kernel of this operator. So which means the type A mode, so you can forget this term here. Then you will have this term. But this is the ordinary equation motion for the closed system. On the other hand, when this term is non-zero, that corresponds to the type B mode, then we will have the some type B energy mode. So in general, we will have the several type of the mode. That is the propagating mode and the diffusion mode, and the type B propagating mode. So the difference is actually the linear dispersion or quadratic dispersion, or just a damping mode. So there are several type of modes appear in this equation. Then, this is somewhat technical, but we conjecture some possible combination of the energy mode or hydrodynamic mode appear in this equation. So this is not our result. So typically, so let me summarize. So typically, the original type A mode in closed system becomes the diffusion mode, and or typical type B mode in open system still propagating mode. So this is one of our results. On the other hand, ordinary hydrodynamic diffusion mode becomes the damping mode in open system. Okay. So let me summarize. This is summary. So ordinary hydrodynamics, that corresponds to the strong to weak symmetry breaking. The ordinary symmetry breaking corresponds to the weak symmetry breaking. On the other hand, the hydrodynamics is a strong symmetry breaking. And also that we discussed the open system, so where the explicit breaking term appear of the only the strong symmetry. So in that case, open symmetry of the open system, there exists still weak symmetry. Then we derive some low energy excitation and classify the dispersion relation. Okay, thank you very much. Schrödinger. Not Schrödinger equation, but that's a diffusion. So there is an additional I here. Yeah. Yeah. That's a Schrödinger. Yes. Yeah, that's right. Yeah. That's a good question. So honestly speaking, so we cannot restrict the this power because you can model, you can always consider that this coefficient is vanishing or something like that artificially. Because this is just a natural case. Yeah. You can always fine tune the theory. Then power can be different. Yeah. Right. Yeah. So that's that information is just turned to the. Yeah, we don't assume, but that information just turn to the some coupling constant. So we integrating out the environment. Uh-huh. So I think the coupling itself is not so important, I think. Yeah. So in some sense, yeah, if I don't know the result, but okay. Yeah, I think if the coupling is strong, then these coefficient becomes very large. So yeah, but yeah, yeah. Uh-huh. Ah, okay, okay. I see, I see. Okay. Ah, okay. Yeah, in some that sense, yeah, we assume that environment, yeah, yeah, there is some scale separation between the environment and the system. Yeah. Hmm. So yeah, roughly speaking, the environment is really huge. So otherwise, dissipation does not appear. Right. But yeah, right. Yeah. Hmm. Okay. Yeah. Okay.
So it seems that, for example, you write down the hydro equation. Hydro equation is just the conservation of energy momentum.
Yeah, yeah.
How about these language, native with what you talk about?
Ah,
Talk about it seems that it's a citation of the hydro.
no, no, no. Hydro itself contains the low energy excitation mode, like phonon and also the
Yeah, you have a sound.
sound. Yeah, yeah,
Sound,
yeah.
right? You just talk about the Lagrangian.
Lagrangian language. Yeah, yeah, yeah. And also the advantage of the this path integral formulation contains the fluctuation. Actually, this is a fluctuating hydrodynamics. Yeah, yeah. And also the contain the quantum fluctuation, but usually that fluctuation is irrelevant in the many body system.
Is this quantum?
Basically,
Quantum or classical?
both fluctuation is included in this formulation. This is Schwinger path integral, but usually quantum fluctuation is much smaller than the thermal fluctuation.
So in fact, we study about similar fields. We only essentially the scalar field.
Mm-hmm.
Touch, and they also have a mode count.
Mm-hmm.
And in the Brownian phase, we only find essentially propagating modes and
Mm-hmm.
And then the radial mode that
Mm-hmm. Mm-hmm.
So my question is, where did type B propagating mode come from?
You mean upper one or a Schrödinger-like equation?
How I can make it those type
Okay, so example. So actually, okay, this is some model that appear the type B mode. So this is just SU2 cross 1, SU2 cross U1 model with chemical potential. So chemical potential appear here. So so if you expand this Lagrangian, so you have the mu times single time derivative term appear in this product. So the effective, actually you have the single time derivative term that corresponds to this here. Yeah. Then if you complexify the pi 1 and pi 2, that is pi 1 plus I pi 2, that is complex field. That variable obey the Schrödinger equation. Yeah. Okay. Weak symmetry can break. Yeah, explicit break. It depends on the system. So what I want to say is that symmetry in open system is a weak symmetry in Schrödinger formulation, whereas the strong symmetry is explicitly broken. So in general open system, weak symmetry is also broken by interaction. But if you have symmetry in the open system, that should be the weak symmetry. Huh? Huh? So in general open system, so sometimes there is no symmetry. But if you have the symmetry in open system, that corresponds to the weak symmetry in the Schrödinger formalism. But whereas the strong symmetry is explicitly broken. That is symmetry in open system in my definition. Okay. Yeah. Yeah. Critical. Yeah. Yeah. Okay. Yeah. Yeah. So sorry. What's the point? Yeah. If you truncate, in RA basis, if you neglect the higher order of A field, then that corresponds to the classical system. I think so. Yeah. Yeah. I've never checked, but yeah, I believe so. Okay, thank you very much.